Wir begrüßen unseren ersten Referenten des heutigen Tages, unseren Keynote, und wechseln dafür gleich ins Englische. Begleiten Sie jetzt den, ja, man könnte sagen, Chefentwickler von Microsoft Azure auf einer Tour durch die neuesten Innovationen unserer Cloud-Plattform. Erfahren Sie, wie Azure intelligente, moderne und innovative Anwendungen in der Cloud, on-premises oder eben auch im Edge-Bereich ermöglicht. Ladies and gentlemen, please welcome the Chief Technology Officer for Microsoft Azure at Microsoft, Mr. Mark Russinovich.
Good morning, everybody. It's great to be back in Germany. My last time in Germany, without counting going through airports, was 2003. Was in Munich in 2003, so it's great to be back. And I'm excited because this time I get to go to Oktoberfest. Good timing for this trip. So this morning I've got a talk on Azure innovation for you, and I've got a lot to pack in. I want to start by framing what I'm going to be showing you, which is just a sampling of the innovation that we're working on at all layers of the Azure Cloud Platform. So don't come away thinking, hey, this is all they've got, because this actually, if I gave you the full presentation of all the innovations that I'd love to be able to talk to you about, we'd be here for half the day or the whole day at least. One of the things that I want to talk about first, and just in terms of innovation, is actually scale is innovation. Achieving the kind of scale that we're at, where when I started in Azure in 2010, we had 40,000 servers deployed. And now we've got literally on the order of 10 million servers deployed across the world in 65 regions, and continuing to grow as we build new regions out in new countries. But we're also building our infrastructure within regions at a massive scale. So data centers continue to grow, not just in the new regions, but also in existing regions. In the next 12 months, we will be turning online between 100 and 150 data centers. So approximately one new data center every 3 days has its lights turned on and customer workloads running in them. You can also see our global fiber network. This is our black dark fiber that connects all our regions together so that customer data is always going over the fastest routes between our Azure cloud regions. But another way to look at scale is not just the physical scale of Azure, but the logical scale. And so this slide, you can see some of the numbers behind the services that are running across Azure. You can see storage, and these numbers, by the way, are from 2022, from about a year ago. You can see storage, 940 trillion transactions per month. You can see the intelligent data platform, 27 exabytes of data being managed for analytics. And the numbers you can read across that chart. This is from last year, like I said, and I've updated the slide for this year's number to give you a comparison for how fast logically we are growing. And you can see, for example, from 940 trillion transactions to 1.1, whatever that number is, 1,000 trillion transactions. But the big jumps are there, you'll see, are on the right side. With security, the number of security signals that are processed every day. The massive jump there from 1.2 trillion to 1.9 trillion. And then, no surprise, machine learning. The number of machine learning operations that are served on a month from 28 billion a year ago when AI was big, but this year, 470 billion. So you can see that AI's kind of exploded in terms of popularity in the Azure cloud. Now, one of the things we want to make sure is, as we're expanding out worldwide, is that we're taking care of the environment, that we're being efficient to bring costs down, and that we're also being green. This slide shows you our data center journey from back when Azure started, and actually before Azure started, when Microsoft started in cloud services building and operating their own data centers. The number that you're looking at here is PUE, which is the industry standard metric for useful watts of energy that actually serve an IT workload powering a server. The closer you are to 1, the more efficient you are, because that means every watt coming into the data center is actually doing useful work, at least powering a data center without any loss. And you can see that our PUE numbers have continuously been driving down from 2.0 when we started down to 1.1, between 1.1 and 1.12, which we believe is cloud and industry leading in terms of PUE. And this is all through a combination of making sure that our data centers are designed more cleanly, that the power is being distributed more efficiently into the data centers. We're taking advantage of things like adiabatic cooling, and we're also deploying over provisioning our data center power with our own workloads, which can tolerate lower availability, such that they can be evicted if, for example, utility power is lost and we need to turn over to generators. But speaking of generators, that's something that we have not liked because they're diesel powered, they're unreliable, they're not very friendly to the environment with their exhaust. The fact is that we've got to have them to deliver the 5 nines availability of our data centers. Back in 2013, we started exploring how can we replace diesel generators with something else, where when the utility power is down in the data center, we can fail over from UPS in that transition to backup power until utility power comes back. And about 5 or 6 years ago, we started to explore hydrogen fuel cells, which are also called proton exchange membrane cells. With this, the fuel is actually water, and this is converted into electricity. The only exhaust is steam, so extremely friendly to the environment. And like I said, back in 2019, we started to deploy these at small scale. This is not something that we could simply go to the market and buy these things because there's not been any demand for this type of fuel cell at the scale that we need them in the Azure cloud. So you can see, working with our hardware suppliers, we started to build out prototype systems at 10 kilowatts, 50 kilowatts, and then in 2019, we brought online 250 kilowatts and were able to power servers for 3 hours with that. Of course, that's far from the scale that we need to be able to put this into production in Azure. But we continue to make advances. And last year, we brought online a 3 megawatt facility with hydrogen fuel cells sitting in container storage tanks to power IT workloads for longer periods of time, for days at a time, which is what we'd expect if there was a long-running utility power outage. And this, you can see in this video, pouring water in, and then the only exhaust is steam. Like I said, we're not quite yet at the level of ready to bring this to production at massive scale, but you can see the kind of long-term investments we make in innovations like this that are good for cost and good for the environment. Now, the next thing I'll talk about is our servers. This is another place where we continue to make advances. And one of the challenges that we've seen coming at us is the rise in power requirements in a server's form factor. You can see the number of watts, the amount of watts that CPUs are demanding to run at maximum performance, and GPUs are even more demanding. You can see the A100 GPUs there, around 400 watts, 400 watts of power for one A100 GPU. The next generation of NVIDIA GPUs, which are coming online right now, 750 watts. And so how do we cool this efficiently? Because what this means in an air-cooled data center is the number of watts you can power demands a certain amount of floor space to allow enough air volume to go through and cool it. How can we pack our servers more densely, which will provide us several benefits? Lower data center footprint, which is of course good for cost and good for the environment, as well as more densely packed servers, which is good for performance. And so we've been investing for years now in alternate cooling technologies. Now, one of the technologies that we've been deploying for specialized hardware is cold plate cooled servers. And this is like what you might have at home, like I do in my GPU cold plate gaming system, which I can overclock. This is actually an example of our own cold plate designs, which are more modular and flexible, that we're deploying in our data centers today. But we're also working on other types of liquid cooling, ones that are even more efficient than cold plate and more flexible than cold plate because they don't have to be designed on a server by server basis. What we've standardized on at this point is one-phase liquid immersion. And you can see here the customized server blades that we've designed, which fit our standard server mainstream fleet servers. These get dunked into a tank, and then the liquid evaporates. And this liquid is non-greenhouse affecting, requires no water consumption, so it's really green for the environment. Plus, we can save 15% on electricity using cold plate and bring the PUE down to 1.05. So 1.05 compared to where we are at 1.1 to 1.12 is a significant drop in the PUE. And the closer we can get to 1, like I said, the better. We're also working on accelerating our servers. and making them more efficient. The CPUs are the most expensive part on the server, and their general purpose, they run the workloads that customers deploy on our servers, but a lot of the computation supporting a server, like processing network packets, processing storage traffic, is much more specialized. And by developing custom hardware to process that, we can be more efficient and lower cost and higher performance. And so since 2013, when we introduced Azure accelerated virtual networking with FPGA offloads for our network packet processing, we've continued to advance our offload technologies. And this summer, we announced Azure Boost. Azure Boost is an offload card that's separate from the server. And this is where the network and storage traffic is actually processed. The CPUs are dedicated then 100% to customer workloads, as well as some of the management software that runs still continues to run on the server. You can see on the offload card, though, that's where we have agents that are setting up network connections and storage connections. But all of the traffic actually gets processed by FPGAs and supporting accelerators. And here's a look at the architecture. Like I said, we've chosen to use FPGAs. One of the benefits of FPGAs, field programmable gate arrays, is they're not software, they're not ASICs or fixed function hardware, they're flexibly programmed hardware. So you get a lot of the benefits of programmable devices like a CPU, but also some of the benefits of custom hardware in terms of performance and power. And so this is what we've been working on, and you can see there that the way that the servers connect to the FPGAs and the system on a chip, which has the ARM cores as well as the memory that goes with it to support it, the agents and the other management software. Those, you might have seen the term RNEC there, that's for RDMA network adapter, because the traffic on our backend and our networks underneath the servers is all RDMA, meaning direct memory transfer across the network from one server to another. Here's a picture of the Azure Boost card. And so you can see the fan there's on top of the ARM complex, those fins there, the cooling fins there on top of the FPGA. And we're already taking advantage of the programmability of these FPGAs, because last year we introduced a line of VMs, the EBS v5 line of VMs. And this line of VMs provided 160,000 IOPS per second, 100 gigabit network. We've just recently upgraded and are in the process of rolling out the upgrades across our fleet automatically with just software updates to the FPGA and the software on the SoC to raise the performance of everybody's EBS v5 VMs by 2.5x when it comes to remote storage performance, and 8x over which is 8x over the previous generation, the v4. So customers don't have to do anything. They don't have to pay anymore. It's the same VM type, it just suddenly has better performance. And just to show you that better performance, here's a little demo that we've got here of two VMs, EBS v5 before the upgrade, EBS v5 after the upgrade. And this is a little utility that just drives storage traffic to the disks on the VM as hard as it can. And you can see 160,000 IOPS per second on the left, and on the right after the upgrade, we're getting that 400,000 IOPS on just without any hardware upgrades, just with the software upgrade to the FPGAs. And we continue to make advances. So you'll see new versions of Azure Boost. Networking in the data center is going from 200 gigabits per second to 400 gigabits, and then we already have line of sight to 800 gigabits per second. This here just shows you another example of a benchmark test that just drives the bandwidth on the servers. And so like I said, this is where you're going to see on the left side, the old VM. On the right side, you can see the 10 gigabytes per second there of storage traffic on the right. Now, we need to deploy infrastructure that's low cost and high performing, but we also need to make it reliable and available. And this is what comes with something we call AIOps inside of Azure. Some of you might be familiar with AIOps. How do you run your IT workload with the help of machine learning that gives you insights? And we would not be able to run at the kind of scale that we're at without AIOps. We just can't have humans going and looking at signals and trying to figure out what's going on at the massive complexity and scale that we've got with hundreds of cloud services across many data centers and regions. So we've been investing over years in advanced systems that will help us understand when something goes wrong. And this system, which started to really come online a few years ago, is called Brain. Kind of the brain of the operations of our cloud. Brain takes in signals from all aspects of cloud operations, from the customer experience. So social media feeds come in and get mapped onto whatever particular services that customers have as a signal of something might be going wrong. We take signals from Azure services. We take what are called service level indicators off of them and try to understand and look for anomalies at massive scale, specific to even particular data centers. We look at the infrastructure device signals. So this is our HVAC systems. This is the data center power and the network physical connections that go through the data center. All of that is wired up. All of that is fed into Brain. And we take Brain, and what that allows us to do is automatically diagnose a problem. Not just automatically diagnose a problem, but pinpoint the cause of the problem. One of the challenges, again, at this scale is when something goes wrong at some layer in the stack that's low, it affects lots of services. And so that means lots of alarms are firing all over the place. And in a fog of war, which in the early days of Azure we would have when, okay, so lots of these services are showing red, where's the actual problem? And it would take us significant time to figure out where it was. Brain can look at everything together, understand dependencies. Hey, this top of rack router has a fault that's affecting these servers, which it has affecting these VMs, which is affecting these services that are on top of those VMs, and immediately pinpoint, hey, it's not these services that are at fault, it's the network devices on this rack. And so immediately we can start to initiate repair processes for something like that. And so you can see all of the use cases that we get out of the system. Like I said, we've been running this in production for a few years and we continue to make improvements. So we're not happy with the numbers you see here, but they're major improvements over the previous kinds of systems that we had in place. 72% time to mitigate reduction. So this means Brain can automatically detect a problem that's reducing our time through automated systems and occasional manual systems to go repair an issue. 58% time to notification reduction. You can see also Brain has very high precision and accuracy, meaning when there's a problem, Brain knows there's a problem. So like I said, this is an area we continue to innovate on. AI Ops is becoming something that is just expected at our scale, and we're also working on actually making AI Ops through Brain available to our customers, where it can take signals from your own services and let you know when something's going on with your service. Now, another way that we want to improve reliability and availability is through not causing downtime for our customers when we need to do upgrades to the software infrastructure of the data centers. We've been building out over the last decade a number of different tools that will allow us to upgrade parts of the server infrastructure with minimal impact to the workloads running on those servers. You can see everything from a microcode update, which might need to be applied to the CPUs on the server, to updating the whole operating system that is supporting the virtual machines on those servers, and the kinds of times that we've got. And so depending on the issue, it's a reliability issue, it's a security issue, or we're adding a new feature, we can pick the tool that's going to have the minimum impact on customers. We want to drive everything down to as close to zero as possible. So we continue to innovate and re-architect the server, so that server software on the servers, so that we can apply even full infrastructure upgrades with no downtime to the servers. One of the key tools that we've been working on to support this is Hypervisor Hot Restart, or HHR we call it. Many of the security fixes or reliability fixes or enhancements to capabilities are centered in the hypervisor supporting the virtual machines. And so we want to upgrade that, and it's also the foundation for upgrading the software above it in the host operating system. So we want to upgrade the hypervisor with no impact to the customer workloads. And with HHR, what we do is stand up a new version of the hypervisor side by side with the old one, transfer state from the old one to the new one, and then shut down the old one, and the new one picks up and starts managing those virtual machines. And I've got a demo here. This is Azure server with 4 virtual machines on it. The left side is the host, and I'm kicking off a batch file that is going to upgrade the hypervisor. The 4 machines are all pinging their own local network address just as fast as they can. And you can see the kind of latency here. It might be hard to read from the back. It's about 6 milliseconds, 7 milliseconds. But when we do the hypervisor hot restart, you'll see a small spike up to about 100 to 200 milliseconds. That's an impact that almost no workload is affected by. And so this is basically transparent upgrade of the hypervisor underneath those running virtual machines. And this is something that we'll be rolling out in the very near future across the fleet. So I just wanted to give you a taste. There's lots more going on behind this to minimize impact of software upgrades, but HHR is, we think, innovative and is going to provide major improvements in our ability to keep the fleet fresh without impacting customers. So let's get on to AI, which I think probably a lot of you are been waiting for. How many of you have used ChatGPT? How many of you use ChatGPT every day? Just out of curiosity. So quite a few of you. How many of you use GitHub Copilot? How many use Copilot every day? How many of you find yourselves more productive with GitHub Copilot? So quite a few of you. So my personal story with GitHub Copilot, which I've been working on machine learning projects on the side, and it really has transformed the way that I code. I've been a coder forever, worked on the sysinternals tools that some of you might know about. What GitHub Copilot has made me is a lazy programmer. And it's actually, it sounds like a negative. I view it as a positive because my goal in life now is to not write any code, but to have GitHub Copilot write it for me. And so I spend a lot of my time in the inner loop of developing code now, telling GitHub Copilot what I want, checking to see what it spit out, just doing a quick code review on it. If it looks good, trying it. If there's a problem, telling GitHub Copilot it made a mistake. Having it apologize to me is always nice. And then applying the fix. And even when it kind of can't get it right the first time, it's always faster than me having had to go and write this grungy code that is just like, I know what I want to do, but I've got to write all this syntactical code to make it happen. GitHub Copilot takes that away from me. It is truly transformational. So if you haven't tried it, or if you have, you might already be aware of this, but this, without a doubt, is changing software development. And there's no going back, and it's just going to get better and better. So at Azure, GitHub Copilot's a representation of a large language model that has been continuing to evolve. Initial versions of GitHub Copilot based on GPT-3, a model that came out a few years ago. But as these models have gotten bigger and bigger, new capabilities have emerged. And it's not just coding that Copilots are great at. As you know, with ChatGPT, or with Azure OpenAI, or with Copilots for M365, if you've gotten onto the previews of that, your documents get written automatically for you. Your emails get reviewed for you. Your Power BI dashboards, it helps you create them just with you telling it what you want. It's transforming all aspects. And if you're not thinking at your company how I can take advantage of large language models, Copilots, develop your own Copilots for your own domain, then you're going to be left behind. This is something that Satya came to the company when we had our GPT-4 moment and said, everybody at the company, no matter where you are, think about how you can apply large language models to whatever you're doing. So not just in our Copilots, customer-facing Copilots, but even in Azure. Incident management, I mentioned earlier with Rain. When there's a live side issue, we show up on the bridge, we call it, to troubleshoot with the other people that are looking at the problem. In the past, it's been look at the Teams chat, try to figure out what the current state of things is. Now it's ask our Copilot, give me a summary of where we are. And it looks at the transcription of the chat, the transcription of what people have said on the bridge, and then provides a summary. And so the incident responder is able to come up to speed instantly. Now, compute for these large language models has continued to grow exponentially for AI in general. You can see this chart kind of showing this exponential curve. GPT-3, 175 billion parameter model, taking weeks to months to train across a vast number of GPUs and servers. GPT-4 even bigger. Well, how big? We actually disclosed the size of the system. So some of you, or most of you, are probably aware that we're the exclusive partner with OpenAI, and GPT-3 was trained on Azure's infrastructure. This is the size of the supercomputer that we created for OpenAI to train GPT-3. 285,000 cores, 10,000 GPUs. When we deployed it, it was the largest supercomputer in the public cloud and the 5th largest supercomputer by running anywhere on-prem or the cloud in the world. GPT-4, we created a supercomputer for OpenAI to train that. That's even bigger. How big? I can't tell you. It's even bigger. But you can imagine GPT-4, OpenAI doesn't publicly disclose the size of that model or the amount of training data that was used to train it or the length of training, but you can imagine it's multiple times bigger than what GPT-3 was. And we created a custom infrastructure for OpenAI that creates a connection of servers with InfiniBand backend networks to connect these servers together, because this training job runs over many, many servers, many, many GPUs. Those servers have to be connected with very high-speed links. One of the aspects of the way that we develop software and services and infrastructure at Azure is a principle that we call 1P equals 3P, meaning if we develop it for ourselves, we want to make it available to our customers. And the infrastructure that we've created for OpenAI is available to our customers. The only difference is the scale of the InfiniBand network, the size of the cluster connected with it, is smaller for our public customers than this massive AI supercomputer we built for OpenAI. Otherwise, it's exactly the same. So this is a look at the GPT-4 training cluster servers, but this could easily be, without any difference, a view of a public rack of GPUs. Those blue cables that you see, there's those light blue cables on the side, those are the InfiniBand network cables connecting all those servers together. And this servers are available to customers, like I said. The HD100s, which is NVIDIA's Hopper generation of GPUs, it's the next version after the A100s that GPT-3 was trained on, are available to our customers soon, and they're in preview right now. And you can see the size of these things. There's a single H100 GPU, has 80 gigabytes of HBM3 high bandwidth memory to support the AI model weights and the tensors that get processed as they're performing computation. They're connected 8 on a server with NVIDIA's NVLink high-speed local networking. And then, like I said, they're connected server to server with NVIDIA's Quantum 2 InfiniBand networks, 400 gigabits of throughput per InfiniBand network at low microseconds latency between servers. Because there's 1 per GPU and there's 8 GPUs in the server, that's 3.2 terabits of networking, bisectional non-blocking networking between the servers in these clusters. And that is what powers large-scale AI, both for training and inference. Now, the software stack that's above this is also something that we innovate on. A lot of people think, hey, things like Copilot and Bing Chat, that's just you hosting GPT-4. It's actually a lot more than that. It starts at the infrastructure, like I told you, with the hardware. There's software services that are AI aware that run on top of that, something we've created specially for AI called Project Forge. I'll talk more about in a second. Then there's the stack that we co-developed with OpenAI. And it's in this stack that you can see the model replica there at the bottom. That is actually GPT-3.5 or GPT-4, whatever version. And then there's a bunch of software services for serving that model that we've co-developed with OpenAI. And above that, then there's a lot of functionality that we've added ourselves to make a user interface and experience that's safe and efficient for our customers. So things like cross-region routing. So when a request comes in, we send it to the right AI cluster for serving. At the heart of this, like I mentioned, is Project Forge, supporting all of this. And Project Forge has a unique because it's a global scheduler. One of the problems we had at Microsoft is GPU capacity that would get locked up. Individual teams or services would get their own GPU capacity, and that meant that it wasn't usable by anybody else. So GPU usage would be fairly low, 50 to 60%. Project Forge aims at making most efficient use of GPUs. Its idea is that it's going to have a global pool of GPU capacity for both customers internally and externally with different priority levels. So you can get your reserved capacity. You get that reserved capacity based on where that capacity can reside, and Project Forge will figure out which AI clusters can meet your needs, evicting lower priority workloads if necessary. But if higher priority workloads aren't running, letting the lower priority workloads run. And with that global common pool that we're currently onboarding all of Microsoft services onto, we go from that blue line of utilization, like I said, around 60%, up to 80 to 90% of GPU utilization. And this is through the power of this global pool of capacity. And you can see previously, every department has their own fixed budget, fragmentation. If they need more, they're out of luck. If they're not using it all, that GPU capacity is idle. But with global common pool, the customers, first party or third party that are premium customers, don't have these walls of capacity, and these lower priority workloads can go and soak up anything that's not being used. And that is being rolled out right now, like I said. Now, the other thing about Project Forge is it's aiming at improving the reliability of large-scale AI, specifically for training, where these jobs are synchronous jobs. They run at the scale of OpenAI workloads for weeks, literally months. And any failure of a GPU means that you got to go back to and start over whatever you were doing that you hadn't saved. So these models have something built into their training loops called checkpointing, where they were every 15 minutes or so, they will save state. And if there's a GPU failure now, they only have to go back on average 7.5 minutes, pick up where they left off. But that checkpointing code, which OpenAI engineers are really good at writing, is very complex. And for most data scientists developing code, writing checkpointing code is cumbersome, error-prone, and complex. And plus, once they write the code, they fix interval for checkpointing that might not be optimal for the cost performance that they want to get based on the size of whatever the checkpoint is. So Project Forge is introducing something called transparent checkpointing, where the developer doesn't need to do anything. Project Forge is just simply told, this is the period of checkpointing you should take, and it can take checkpoints automatically. And we've been working with NVIDIA and AMD on automated checkpointing technology, which means saving the state of the GPUs that we then rehydrate. The fantastic thing about this technology is that it means that when a workload needs to get evicted because a higher priority training job comes in, we can simply checkpoint it. In fact, we cannot necessarily just put it on the side and have it sit there until capacity comes back in the cluster it was evicted from. We can actually migrate it. Again, with the global common pool, we can say this training job, which is running in Europe North, can move to Europe West, and we can do that migration automatically without the developer of the AI workload having to do anything. Project Forge takes care of all the details. And that is going to be another boost to utilization of our AI infrastructure. But just an example, again, of the kind of innovation that we're doing, and there's a lot more. The transparent checkpoint in this slide just shows you, it's a very complex task, as well as take into account the intricacies of the optimizations used in large-scale training with something called 3D parallelism. Now, finally, I want to talk a little bit about confidential computing. So, one of the concerns customers have had since I started in Azure in 2010 is, can I trust the cloud with my data? And many customers have extremely sensitive data. Back then, people didn't really trust the cloud at all because it was brand new, and so they weren't unsure of what was going on behind the curtain. And so we built up customer trust. And actually, Microsoft, I think, has been a leader with trust in the way that we handle customer data. Customer data is customer data. It's private to them. We don't look at it. We don't train on it. We don't move it. If the customer puts data in a particular region, it stays in that region. We want to make sure, we've done this with lots of logical controls, that Azure operators don't have access to that data, that somebody breaking into the infrastructure can't get access to that data. And this continues layers of defense and depth all the way down to the physical data center security. But we are not satisfied, because when we talk about the protection of data, what we've had, and we've been continued to evolve and mature in Azure, is encryption to protect data. So even if somebody gets access, they don't actually see the data. And everybody's familiar with encryption of data at rest and encryption of data in transit. kind of interesting thing is when I started in Azure, there was neither of these were expectations by us or customers. Nobody could think today of sending unencrypted network traffic. Now TLS is just an assumption. Like if you don't have encrypted network connection, then you're doing it wrong. And everybody just assumes encryption. And the same thing when it comes to encrypting data at rest in the cloud. We've got automatic server-side encryption. You can bring your own keys with customer-managed encryption. But what's been missing is protecting that data while it's being computed on, because the keys go to the servers decrypt that data, and then they perform analytics or AI on it. And while that's being done, the CPU state, the memory, has that data in the clear. This is a vector that we want to close off. We want to make it so that even if somebody gets access to the server, logical access, even physical access, that they cannot see what's going on in that computation. It's the missing piece of protecting data through its whole life cycle. And that's what confidential computing is. It is protecting the data while it's in use. And it does this with hardware support. That hardware creates something called a trusted execution environment where that data is basically in a black box. Not even the administrator of the system, the hypervisor can't get access to it. Nothing can get access to it. And what makes this really useful is that the hardware can measure what's in that black box and have a attestation report that it signs that can then be presented to a client, another piece of software or a person that is looking at releasing an encryption key or decryption key to the software running inside that enclave. They can establish trust. Is the software running inside the enclave? Is it software that I trust? Is it the code that I wrote or that I audited? And if so, I'll release the key to it because I know that it's going to protect that data, and I know that data is being protected by the hardware around it. Microsoft has been a pioneer with confidential computing. We actually coined the term confidential computing in a paper that we wrote back in 2015. We created the Confidential Computing Consortium, and we've been working with NVIDIA, AMD, and Intel, and ARM on driving forward confidential computing hardware standards and pushing them to give us confidential computing hardware. You can see we've been the first to announce every new innovation in confidential computing hardware. The first to launch with these partners and the first to deploy it in our data centers. And last year we were the first to announce a preview of confidential GPUs with NVIDIA, very relevant for AI, of course. And we're now going to have, launching with our H100, the Hopper GPUs with NVIDIA, confidential Hopper GPUs as well. What this means is that you will have the ability to do confidential AI and analytics using GPUs where the data is protected through its whole life cycle. Goes into the confidential virtual machine, protected with that hardware box around it. The virtual machine transfers data to the GPU, protected with an encrypted link. The GPU protects it as well. Computations performed, the result comes back. And whether you're doing AI training or inference, that data is never outside the protection of the hardware. I've got a really quick demo here showing you this and the software capabilities that we've developed inside of Azure that make this a reality. This little example here is a confidential container, so serverless container that is running a little workload that gets encrypted cell phone IDs. Scenario is there's a store, people are walking in the store. We want to be able to offer them targeted offers if they're a customer that's registered with us. So there's a system looking at cell phone IDs as they're being broadcast, encrypting them, sending them into our database system, which is then looking up, being able to decrypt those messages, and then look in a database to see if the customer is one of the customers of the store. And so let me run that demo really quickly. Now here, I've just kicked off the client side, which is sending in the cell phone messages encrypted. So that's the encrypted IMEI strings. Looking at event hubs where we can see those encrypted messages that are sitting there because I don't have anything processing them yet. And the next thing I'll do is launch a container, a confidential container that's going to be protected by AMD's SNP hardware. And that confidential container has this code in it that is able to decrypt the IME message, look in the database, and then tell us if there's a match, if that customer is one we should offer something to. This is the Helm chart that launched, the Kubernetes manifest that launches that confidential container. And one thing to notice here is the only difference between this and a non-confidential container is this section right here, which says this thing is going to be protected by AMD's confidential computing hardware, and it's going to have this signature on it that will allow it to get the decryption key. So only if it's running in the enclave, only if it's this piece of software will it have access to the key. Now I launch the container, and we can see that it's able to, it's starting to process the logs. We're going to take a look at the logs here. It's showing you the encrypted IME messages, but it's able to say, hey, this is a customer in the database, or it's not. And so there's one that's not, and here's one, another message, and you can see this one did match to known IME data set. So again, customer privacy protected, end-to-end, no operators, no hackers, nobody gets access to what's going on with these customers. And so confidential AI, which we're making a reality, all these scenarios. One of the concerns that we have customers telling us is, when I'm sending prompts into Azure OpenAI, that's very sensitive information, and the results are too. We're working on protecting it with confidential computing hardware. So finally, I just wanted to show you something fun. This is the coolest part of my job, is having access to the latest, greatest hardware. And one of the things we do in Azure is deploy the latest and greatest hardware. This is a system that we call Mega Godzilla Beast. And we call it that because this thing has, if you can read there, it's got 22 terabytes of memory available to it. And it's got how many CPUs? 832 virtual processors, which is enough to make Task Manager look like a game from the 1980s. And so that's what I made it. This is Task Manager, and I've taken Breakout and made it work on Task Manager. So that's a video recording of me playing Task Manager using the keyboard to move that little paddle along the bottom, that have CPU usage light up on the appropriate core that makes it, you know, like I'm playing Breakout on Task Manager. So, by the way, that game cost, just playing that little snippet right there, probably cost like $10,000. But that's the thing that I get to do at Microsoft. So anyway, with that, I want to thank you very much for hosting me. Just give you a taste of innovation all across the stack. So I covered things from our data centers to our server hardware and accelerated offload, to on up the stack into AI infrastructure, AI hardware, AI services on top, the way that we try to utilize capacity more efficiently into confidential computing. And with that, I want to thank you up. And I think we've got time for a couple questions.
Yeah.
Thank you, Mark.
Mark, I'm a nerd at heart, and you did the job that normally the coffee has to do for me in the morning. You energized me so much. Thank you so much. Really great presentation. And before we conclude, we have a few questions for you that came through the chat. The first one is, great to see all the valuable insights around AI innovations that are coming from Azure. Your personal perspective has been asked on what is next with generative AI, and how is it going to shape up our world?
Yeah, I think, so what's next? It's really hard to predict. Things are moving so fast. I already gave kind of an insight into my the impact of AI personally on me through Copilot, GitHub Copilot, which like I said, convinced 100% that's transforming software engineering and making developers more productive. By the way, surveys show that developers are 40% more productive with GitHub Copilot. But as far as where things are going, it's really hard to say. The pace of innovation when it comes to AI is actually accelerating. And AI is being used to make AI even better, is the kind of accelerant that we've got here. How many people have seen the new announcements from OpenAI around vision-enabled GPT-4? So if you haven't seen it, you need to go check it out, because it's absolutely mind-blowing what the combination of imagery and video and GPT-4 can do for you. And while it's kind of cool just to see, hey, you can give it a picture and say, GPT-4, what's in this picture? Or you can say, GPT-4, create a picture like this. No, move the dog to the left. Is thinking about the applications and business scenarios. So I was just meeting with customers in the UK, retailers there, who are seeing uses of this from everything from looking at quality control of the products that come into their warehouses through having GPT-4 analyze images and tell them what's wrong with the products, or if they match the descriptions on the manifest, to checking marketing images, so the images that are created for the website, making sure that they're actually accurate. And that's just a taste of things. So it's like hard to say, but it's just a lot of innovation.
More efficiency.
Yeah.
So, okay, great.
There were some other questions in the chat about, Mark, how can we start? How can we get ready and get prepared for this new, I think it's fair to say, revolution? So do you have any tips for that?
Yeah, I think my tip is to whatever organization you're in, to drive the mission that Satya gave us all back in the early spring, which is no matter what you're doing, go learn about this, go play with it, and think about how you can use it to improve your process, your customer experience. You have to understand what's capable, and that it's going to spark ideas. I mean, just go take a look and it'll start to spark ideas. But if you're not doing it, if your company is not actually figuring out how to do this, your company is going to get left behind. And that's a message that I want to leave you, because again, talking to so many customers that are sitting here at the forefront, already integrating this technology, and really just improving productivity, improving quality of their whole customer experience and their whole processes. It's kind of flabbergasting.
I love the go bold.
Yeah.
Go bold with AI. That's the message, right?
Yep, exactly.
Thank you very much. Thank you, Mark.